Okay. Today we will performing the sixth practical of the subject electrical drives. Okay. The aim of the experiment is open loop speed control of six-step inverter fed induction motor drive. Okay, means what? Here we are using six-step PSI to control the speed of the induction motor. Okay. Okay. By using any control algorithm or by using any method like six-step inverter or PWM inverter, okay, they should satisfy one thing, that is the V by F ratio should be constant, okay, to maintain the maximum flux capability which governs the maximum torque capability. Okay, so the V by F control or V by F ratio has to be controlled. Okay, so in six-step VSI, the inverter is only able to vary the frequency. Okay, so this three-phase inverter will vary the frequency of AC voltage given to induction motor. Okay, but it is not able to vary the voltage amplitude of the AC waveform. Okay, which depends on the DC link voltage. Okay, this is the DC link voltage at the input of the inverter. So we require extra circuitry to vary the AC voltage by varying the DC link voltage, and for that three-phase full converter is used. So three-phase full converter will vary the DC link voltage VDC, okay, and thereby the voltage part of the V by F. Okay, so by varying the DC link voltage to vary the RMS value of or amplitude uh, of the output AC voltage, and by varying the frequency we are maintaining V by F ratio constant. So we will get variable frequency and voltage, okay, at the output of this inverter. Okay, so this uh, inverter, we can say that it is a variable frequency and voltage inverter. Okay, so I will show how this uh, hardware will be controlled. Okay, so to set the DC link, okay, we will require a DC voltage regulator. Okay, and this DC link DC bus voltage regulator will set the value of firing angle alpha, okay, such that the VDC should be varied accordingly. Okay, if we increase the value of alpha, the VDC will decrease, and if we decrease the value of alpha, the VDC will increase. The bridge firing circuit or bridge firing unit will generate gating pulses, okay, which are given to the gate terminal of this thyristor rectifier, okay, uh, at a delay angle or firing angle of alpha. Okay, and the six-step generator, okay, will control this three-phase inverter like a 180-degree mode of conduction. Okay, where if the switch is turned on, it will be turned on for next 180-degree duration, and after each 60-degree, one of the switch is going to be turned off. Okay, here at any time three switches out of the six, okay, will be turned on. Okay, now I will show the detailed control strategy for this type of drive. Okay, so the six step VSI, okay, it requires a thyristor rectifier, okay, which converts three phase AC into DC. okay, and this is given to the inverter, okay, 6-step inverter through this LC filter. This is a inverter, maybe IGBT based inverter is used. Okay, so this is a rectifier circuit and this is inverter circuit, and this inverter will generate AC voltages which are given to induction motor. Okay, so this inverter is able to vary just frequency, and this rectifier will able to vary the voltage. Okay, so we have to control inverter and rectifier both at a time, and we are performing experiment, okay, which is a open loop system. Okay, read the aim of the experiment: open loop speed control. Okay, means what? We are not taking any speed feedback. We are not taking any speed feedback. Okay, means we are not sensing the speed of the induction motor. So in like open loop system, okay, we have to convert the command which is given to a appropriate signals, okay, which will control the inverter and rectifier. So here the command will be the reference speed, okay, which will be converted into frequency using the relation 120 f by p. Okay, the number of poles is known. Okay, for known number of poles we can calculate the frequency f star. Okay, and from this f star, okay, using the lookup table or flux control block, okay, this is a flux controller or flux control block, or we can say it is a lookup table, bracket lookup table. Okay, a voltage magnitude will be selected, V star. Okay, so we have the value of V star, okay, which should be there in a DC link, okay, or I will write, instead of V star I will write VDC star. Okay, because we are changing voltage given to the induction motor by changing the DC link voltage, so I will write VDC star. Okay, so we have two signals, one is the F star and other is the VDC star. This F star can be converted into theta. Okay, it is converted into theta, okay, because we know that theta is equal to omega t, that is, therefore d theta is equal to omega dt. Okay, therefore omega is equal to d theta by dt. Okay, or we can use, okay, d theta is equal to omega dt, or we can use this sim, there should be a, there may be a clock. Okay, clock is there. Okay, so we have to convert that f star into theta. Okay, I will show you f to theta conversion. The output of this will be the theta. So how this can be done? We know that theta is equal to omega t. Okay, taking derivative of both the sides, we will get theta is equal to omega dt. That is omega is equal to d theta by dt, or omega is equal to theta dot. Theta dot is equal to d theta by dt. Okay, that is integration of omega. Okay, taking integration of both the sides is equal to theta. Okay, therefore by taking integration of frequency, theta is equal to integration of omega is equal to integration of 2 pi f is equal to 2 pi into integration of f. Okay, okay, means by just taking the integration of that calculated frequency and multiplying it with 2 pi, you can get theta. Okay, so we have a phase angle theta, and we have the algorithm of 180 degree mode of conduction, 180 degree mode of conduction. Okay, okay. Then depending on what is the value of theta, okay, the particular switch will be turned on. Okay, whether the theta is from 0 to 60 degree, or from 60 to 180 degree, or from 120 to 240, sorry, 120 to 180 degree, then from 180 to 240, 240 to 300, then 300 to 360. Okay, 360 is nothing but what again? 0 degree. Okay, these six sectors are there. Okay, means if the theta is between 0 to 60 degree, then which which switches will be turned on. Okay, for example, 0 to 60, 0 to 60 degree, which is 5, 6 and 1 will be turned on. Then for 60 to 120 degrees, switch number 6, 1, 2 will be turned on. After that, switches 1, 2, 3. Again after that, 2, 3, 4. Then 3, 4, 5, and then 1 minute, 4, 5, 6. These switches will be turned on. Okay, so what is the value of theta decides which set of switches will be turned on. Okay, so here inverter will be controlled. Okay, so it will generate pulses for inverter switches. Okay, again this vdc star, one more signal we have generated. Okay, will be given to a pi controller. Okay, which will work as a dc bus regulator. Okay, the input, other input to pi controller is the actual dc link voltage. Actual DC link voltage. Okay, the error between these two will be given to pi controller. It will generate a control voltage vc star or vc. Okay, it will be given to a cos inverse, or in terms of MATLAB it is known as arc cos. Arc cos means was cos inverse. Cos inverse of vc, it will give you alpha. Okay, and this alpha will be provided to firing circuit. Firing circuit. Okay, and this firing circuit will generate pulses. Okay, which will be given to the gate terminals of rectifier, thyristors in rectifier. Okay, this is how this particular practical control algorithm works. Okay, now we will see. Okay, now we will see actual practical performance. Okay, so today's practical, to open today's practical, you have to go open first MATLAB. In MATLAB, okay, there is an option under this home tab. Okay, help. Okay, in under help, click on examples. Okay, click on examples. When you click on examples, okay, okay, This window will be open. Okay, type here. 1 minute. Okay, I will open once again. Okay, click here, sim power system. Okay, some options will be there. Okay, under category, select sim power systems. Okay, when you click on that, okay, the sim power system examples will be turned on or open. Then click on examples. Okay, example option is there. Okay, when you click on examples, there will be two options: Simscape components and specialized technology. Again, click on specialized technology. Okay, when you click on specialized technology, number of options will be there. Okay, out of that, click on again electric drive models. Okay, under electric drive models, select the practical named AC1 6-step VSI induction 3 HP motor drive. Okay, click on that. When you click on that, okay, such window will be open. Okay, that practical will be open. Okay, then click on open this example. Okay, so that MATLAB simulation will be open. So now the MATLAB simulation is opened up. So we will perform the practical. Okay, so how to perform practical? For that we will see the observation table, what type of readings we should take. Okay, so first observation table is a performance of drive at variable speed with constant load torque. Means what? The load torque you have to maintain constant equal to 10 Newton meter. You have to given it a constant value. Then you have to change the reference speed command and take this reading. What is the actual speed for that reference speed? Given reference speed. What is the DC link voltage? What is the minimum value of torque, what is the maximum torque value of torque, calculate the torque ripple based on those values. Okay, then what is the firing angle. Okay, then what is the DC link voltage. Okay, DC link current, and what is the value of slip, you have to calculate it. Okay, so we will first see. Okay, so you can see here the speed reference and load torque. Okay, they are the uh, they have given the unit step. Okay, first remove those things and connect a constant block there. Okay, click on the symbol Simulink. Okay, this is the Simulink symbol library browser. Click on that, a new window will be open. Wait for a minute. Okay, so under commonly used blocks, okay, constant option is there. Okay, select that and drag that on the practical we have selected. Okay, I will show you. I have selected that and dragging here. Okay, so now you can connect here. Okay, okay, I just magnified the practical. So this first constant is connected to SP. SP means what? Set speed or speed command. Okay, first we are in, reading. For that I will give speed equal to 300 and load torque I have to maintain constant throughout. First readings equal to 10. According to that table, okay, we have to take the readings of current IDC and firing angle alpha, and for that you have to select the block AC1. Okay, 6 step VSI induction motor drive block, that is AC1 block. Right click on that. 1 minute. Okay, right click on that, then select the option mask. Okay, under that select look under mask, so you will open that particular block. Okay, this is the block. Okay, so okay, we will check, okay, what is the control algorithm we have studied and what is the actual implementation here. Okay, so this is the rectifier, this is the inverter. Okay, so to control the rectifier, the firing circuit is required. Okay, this is the firing circuit, and for to that firing circuit there is one input, okay, which is alpha. Okay, which is coming from here. This is the alpha. Alpha comes from what? A DC voltage regulator. Okay, inside DC voltage regulator there is a PI controller. Okay, similarly to control inverter, okay, the set speed, okay, speed command, okay, should be converted into frequency command. Okay, appropriate frequency command, and that frequency command is converted into VDC star or VBus star. Okay, which is given as an input to the DC link DC bus voltage controller. Okay, and again that EF is converted into frequency is converted into theta, and that theta is converted into pulses. Okay, so all these things are there in that block. Okay, one more, there is a braking chopper they have used. Okay, which uses dynamic braking. Okay, means what? Whenever there is a regeneration action, okay, when the actual speed of the motor is greater than the synchronous speed, okay, in that case the regeneration may happen. Okay, but here that extra whatever the power is generated, they have wasted in the register connected at the DC link, so you can see that they have implemented dynamic braking. Okay, I will show you. Okay, uh, first this block braking chopper. Okay, you can see here when this chopper switch is turned on, okay, power will be dissipated, okay, in this register. Okay, this is a LC filter. Okay, so we have to take the reading of DC link current IDC. So I will connect a scope here. Okay, but that will not be copied here, so you have to disable this link, disable here. Now you can copy that block here. Okay, so IB, this DC link current is known, is named here as a I bus. Okay, but it will give you instantaneous value of current, but we want its mean value or RMS value, so we have to select a block RMS or mean block. Okay, go for simscape. Under the simscape there is a sim power system. Under sim power system there is a specialized technology. Under specialized technology there is a control and measurement library. Under that there is a measurements option, and in that, okay, mean block is there. Okay, select that and add to the simulation. Okay, so I have added here, so you can now connect these two I bus. Okay, and now the we will get the mean value of this DC link current here. Okay, so here what is the frequency they have chosen for this particular practical is the 60 hertz. Okay, don't change that. Set the sample time as that of the system, okay, which is equal to 2 into 10 raised to 5 2 e raised to minus 5. Okay, again we have to take the reading of what is the firing angle. So for that again you have to connect the scope. Okay, so again now I will show uh, how this speed command is converted into frequency and then in the phase sorry angle theta and then in the pulses. Okay, so for that you have to open the 6-step generator block. I have opened it. Okay, okay, you can observe here the reference speed n star. Okay, it is converted into, okay, this is a uh, speed to, okay, rpm to hertz. Okay, rpm to hertz converter, where that equation, okay, 120 f by p, okay, that equation they have implemented here. So we will get a frequency command here. Okay, here frequency input, and here that frequency input, okay, is converted into theta by taking the integration of that. This is the discrete integration of frequency, and that then that theta is given input to the this gate sequencer or pulse generator. Okay, here you can check the sectors are there. Okay, once a switch is turned on, okay, it will be turned on for 180 degree. Okay, so first uh, for switch 1 sw1, okay, you will observe here. Okay, 0 to 180 degree duration they have given. Okay, 120 to 300, then 60 to 240, means what, each duration is of 180 degree. And also after 60 degree, one switch is going to be turned off. Okay, so 0, then 60, okay, then 120 is there, then 180, then 240, then 300, and again 360, that is 0. Okay, means that particular theory, okay, they have implemented here to generate a gate signals. Okay, so in this way gate pulses are generated, which are given to the uh, base of the IGBTs. Okay, the DC bus voltage regulator I will show you. Okay, the vbus, okay, which is generated from frequency command. Okay, it is given to this PI controller. The PI controller's output is the control voltage VC. Okay, V out or VC. That V out is converted into firing angle alpha by using the uh, arc cosine, arc cos. Okay, that is cos inverse function. Okay, so alpha is generated here, and that alpha is given to what, a firing circuit. This is the bridge firing circuit. So in this way this rectifier circuit is controlled. Now we will perform the experiment. For the first reading, where is the speed reference is 300. Okay, and the load torque is 10 newton meter. Okay, so here the speed is 300 and load torque is 10 newton meter. Now I will run it. Okay, it is running. 1 minute. Now it is compiling. Now, okay, now it is running. For first reading, it will take some time. Okay, after that, it will run fast. Okay, you can observe here the sampling time is 2 into e raised to minus 5, which we have placed at or put in the min block. Okay, now it is run. So what readings we have to take? First, what is the actual speed? Okay, actual speed, it is here. It is shown in this block. Okay. Okay, one thing I have uh, forgotten to do. Okay, in this scope, we have to change the settings in history. Okay, unclick on limit data points. Okay, unclick that point. Okay, here also unclick that option. Now I will run once again. So first reading is, what is the actual speed for the speed command of 300? Okay, you have to take all those readings at when the readings or the machine is in steady state. Okay, so in second diagram, okay, the pink one is the reference command, okay, speed command, and the yellow one is the actual value. We will see it in steady state after point 7 seconds. Okay, steady state is started. So the speed is around, okay, 221. Okay, the speed is 221. Okay, you can see here the speed is 221. Okay, speed is 221. So I will put here 221. Okay, what is the DC link voltage? Okay, here is the DC bus voltage they have given. Just take the what will be the average value you can put by observation. It is around uh, 50 volt. Okay, or here also you can use a mean block. Okay, I will take it as a 50 volt. So DC voltage is 50. What is the torque minimum and torque maximum? Okay, the third graph is of the torque. Okay, you have to take the reading as a steady state. Okay, after 0.5 seconds the steady state has been started. So I will take the reading here. Okay, you can observe the maximum value of the torque T max is around 12.6. Okay, 12.6. T max is 12.6, and the T mean is T mean is 7.2, around 7.2. 7.2. So torque ripple is equal to T max minus T mean divided by the reference. Reference is 10. Okay. So torque ripple is equal to 12.6 minus 7.2 divided by 10, 0.54. Okay, this is the torque ripple alpha. Now we will see what is the value of alpha. Okay, for that you have to look under marks the AC1 block. Okay, here is the alpha. In this scope the alpha is there. Okay, so by observation you have to select, you have to choose what is the average value of this alpha. Okay, it is around 93 or 93.5. So alpha is equal to 93.5. Okay, and for that IDC is equal to, okay, we have to see what is the value of IDC, and for that you have to look under marks the breaking chopper. Okay, there is a arrow sign symbol is there, click on that. Okay, if it is not available then right click and choose look under mask. Okay, so here there is a current. Okay, the current you have to select again in steady state. This is the current. Okay, it is around 9.24. It is around 9.24. Okay, and sleep is equal to reference speed minus actual speed divided by reference speed. That is 300 minus 221 divided by 300 equal to 0.264. 0.264. Okay, so in this way take the readings of first table. In second table, okay, you have to put the speed is equal to 1800 rpm and change the value of the torque. Okay, so I will show you one reading here. So here you have to take the speed is equal to 1800, and for torque I will show for torque 8. Okay, and run it. Okay, just change these two readings. Okay, now it is run. So first reading is what is the actual speed. Okay, actual speed is 1740. Sorry, for load of 8 Newton meter, I have taken the readings. Dieseling voltage. Okay, dieseling voltage. This is the dieseling voltage. Okay, it is around 280. Dieseling voltage is 280 volts. What is the minimum value and maximum value of torque? We take the readings at the steady state. Okay, the maximum torque value of torque is around 12 volt and minimum value is 6. Sorry, take 12 Newton meter and minimum is 6. So the torque ripple is 12 minus 6 divided by 8. 12 minus 6 divided by 8.75. Okay, firing angle alpha, for that you have to look under mass. Okay, this is the firing angle alpha. It is around 31 volt. Sorry, 31 degree. Okay, obviously the voltage, DC voltage is increased to 280, so the firing angle is decreased. Then IDC, for that we have to go inside the braking chopper block. IDC is here. It is around 6.4 ampere. Slip you can calculate. Okay, reference is 1800 minus actual speed is 7040 divided by reference. It is 0.033. Okay, so this is how we have to take the readings, and we have to plot the graph of speed versus sleep, distilling voltage and firing angle for both the readings, for both the tables, and you have to answer these questions. First is the what is the state. First question is state the method of speed control of induction motor. What is the best speed means? Why a converter should be controlled with frequency? Why braking chopper is required? So the nature of motor input current is sinusoidal. Can be thyristor bridge be replaced with diode bridge? Okay, all these questions we have discussed in theory part. Okay, you just remember those things and write down the answers of these questions, and after that write down the conclusions. Okay, we will stop here.